The Pennsylvania State University College of Earth and Mineral Sciences, Department of Energy and Mineral Engineering presents the Electrochemical Lab Instructions for Electronic and Ionic Conductivity, Metals, Strong and Weak Aqueous Electrolytes. Equipment and Materials. An LCR digibridge for impedance measurements. A high-precision ammeter for current measurements. A DC power supply. A high impedance electrometer for potential measurements, an analytical balance and weighing paper, a conductivity cell for measuring the ionic conductivity of liquids, a prepared circuit board with a 126 centimeter copper wire, conductivity standard solution, zero point 0.1 molar acetic acid and solid sodium chloride, a 500 and 100 milliliter volumetric flask, a 50 and 10 milliliter graduated cylinder, a 100 milliliter test beaker, 1 liter waste beaker, a funnel and straw, 10 250 milliliter test solution storage containers, a carboy and squirt bottle of distilled water, disposable pipettes, and a thermometer. Solution preparation. Dilute aqueous sodium chloride. We'll begin by preparing 500 milliliters of 0.01 molar sodium chloride from solid sodium chloride. After calculating the appropriate mass of sodium chloride to be added to the 500 milliliter volumetric flask, use the analytical balance to weigh out the proper amount. Transfer the sodium chloride from the weighing paper into the volumetric flask. Rinse the inside neck of the volumetric flask with distilled water to ensure that no sodium chloride remains clinged to the walls. Using the carboy, fill the volumetric flask to the base of the neck, and then using the squirt bottle, add distilled water dropwise until the proper volume is filling the flask. Give the solution a few moments to thoroughly mix before transferring it to the 250 milliliter storage container. We will now use this 0.01 molar aqueous sodium chloride to prepare the following solutions. We will prepare 100 milliliters of 0.005 molar aqueous sodium chloride from 50 milliliters of 0.01 molar aqueous sodium chloride. We will use the funnel and straw to facilitate the transfer of the solution into the graduated cylinder. Use a disposable pipette to transfer solution dropwise for a precise measurement of the 50 milliliters to be transferred. Again, using the funnel and straw, we'll transfer the solution from the graduated cylinder into the 100 milliliter volumetric flask. To ensure that no solution is left in the graduated cylinder, rinse it with distilled water and then pour that into the volumetric flask. Then, rinse the flask itself with distilled water to ensure no sodium chloride is left attached to the walls. Finally, top off the volumetric flask with distilled water. And transfer 100 milliliters of 0.005 molar aqueous sodium chloride to the 250 milliliter storage container. We will now prepare 500 milliliters of 0.001 molar aqueous sodium chloride from 50 milliliters of 0.01 molar aqueous sodium chloride. Using the same techniques as before, we will transfer 50 milliliters of the more concentrated solution into a 500 milliliter volumetric flask, fill the remainder with distilled water, and transfer to a storage container. We will now use this 0.001 molar aqueous sodium chloride to prepare the following two solutions. We'll now prepare 100 milliliters of 0.0005 molar aqueous sodium chloride from 50 milliliters of 0.001 molar aqueous sodium chloride. Use the same procedure as before to prepare this solution. Transfer this solution to the storage container and move on to the final aqueous sodium chloride solution. We'll now prepare 100 milliliters of 0.0001 molar aqueous sodium chloride from 10 milliliters of 0.001 molar aqueous sodium chloride. Transfer the final aqueous sodium chloride solution to the storage containers and set them aside for later testing. Any waste sodium chloride or solution can be disposed of in the drain. Dilute aqueous acetic acid. First, we will prepare 500 milliliters of 0.01 molar aqueous acetic acid from the stock solution of 0.1 molar aqueous acetic acid. We'll begin by transferring approximately 60 milliliters of the stock solution into a 100 milliliter beaker. Using a graduated cylinder, carefully measure out 50 milliliters of the 0.1 molar acetic acid. Using the same procedure as before, we'll now transfer this 50 milliliters into the 500 milliliter volumetric flask and top off with distilled water from the carboy. Once the 0.01 molar aqueous acetic acid solution is prepared, transfer 250 milliliters of it to the storage container. The remainder can be disposed of in the drain. Finally, we will prepare 0.005, 0.001, 0.0005, and 0.0001 molar aqueous acetic acid solutions using the same procedure prescribed for the sodium chloride solution. Ionic conductivity. Calculating cell constant from the standard solution. First, we'll connect the black and white leads from the conductivity cell to the black and red connections for the digibridge. The red, green, and gray wires from the conductivity cell will not be used in this experiment and can be ignored. Ensure that none of your leads are in contact with one another, then power up the digibridge with the button on the bottom left of the system. Once the system has booted up, we'll need to ensure that we have the proper settings. The top button, F1, will cycle through the frequencies to be tested later in the experiment. The second button, F2, will determine the applied voltage for the impedance measurements. In this case, we'll use the default setting of 1 volt. The third button, F3, has two settings for the left and right. We would like the left side to read ZS and the right side to read theta, the Greek symbol. Simply press F3, then press the left key to choose which setting comes on the left. Use the down arrow to cycle through until it reads ZS. Then press the right arrow to choose the right setting and press the down arrow until it reads theta. We can now transfer approximately 75 milliliters of the standard conductivity solution to the test beaker and carefully lower the conductivity cell into the solution, ensuring that the platinum plates are completely submerged in the solution and being careful not to bang the glass against the side of the beaker. Next, we can insert the thermometer into the solution, and we'd like to wait approximately 1 to 2 minutes to allow both the thermometer to come to equilibrium, and more importantly, to allow the electrodes in the conductivity cell to reach their natural equilibrium. Now that the cell has come to equilibrium, we will use the top button F1 to cycle through 4 different frequencies: 100, 120, 1000, and 10,000 Hz. Record the value of ZS, impedance magnitude, and theta, phase angle, from each one of the frequencies for each solution tested. Give the cell at least 1 minute between tests to come to equilibrium. Ionic conductivity. We'll now test the ionic conductivity of a strong aqueous electrolyte, sodium chloride, and a weak aqueous electrolyte, acetic acid. We can now begin to test the ionic conductivity of each aqueous electrolyte solution previously prepared. We'll use the same test procedure as prescribed for the conductivity standard solution testing. When the test is complete, the test solution can be returned to the storage container, or if contaminated, can be disposed of down the drain. To ensure high-quality results, I would recommend beginning with the dilute sodium chloride solution. After the test is complete, thoroughly rinse both the test beaker and the conductivity cell. Shake out any excess water and then move up stepwise to the more concentrated solution until you've reached the final sodium chloride solution. At this point, very thoroughly rinse out both the test beaker and the conductivity cell, shake out any excess water, and begin again with the aqueous acetic acid testing. I would recommend against cleaning the glassware with detergent in between testing, as even the smallest amount of detergent will greatly affect your results in these experiments. The waste generated by these experiments can all be disposed of down the drain safely. When the final test is complete, we can remove the conductivity cell from the solution, transfer the solution back to the storage container, power off the impedance digibridge, and then it is important to thoroughly rinse out the conductivity cell. Again, it's not necessary to use detergent inside the cell itself. Electrical conductivity. We'll now measure the electrical conductivity of a copper wire. Please exercise caution when dealing with electricity. We'll begin by creating a circuit from the copper wire into the positive lead of the power supply. We'll connect the other leg of the copper wire to the positive white terminal on the ammeter. We'll then complete the circuit by connecting the negative lead from the ammeter to the negative lead on the power supply. We can power up the ammeter using the power button on the bottom left. Once the system is booted up, we can set it to DC current measurement mode by pressing the DCI button. We'll now connect the high impedance electrometer to measure the potential drop across the wire. We'll be doing this on the outside of the connections for the current measurement circuit. Before powering up the power supply, we want to double check that none of the leads are contacting any exposed metal or contacting each other. Next, we'll power up the high impedance electrometer using the power button on the bottom left. Press the zero check button on the top center, and it'll begin giving us the recording of the potential drop across the wire. Turn both knobs on the DC power supply all the way to the left to shut off any current or voltage coming from the system. Then power it up using the power button on the bottom left. We'll turn the voltage setting up rather high, 3 or 4 complete turns to the right, and now the system is in current controlled mode. From this point on, we can control the current flowing through the wire simply by turning the current knob on the DC power supply to the right. Using the readout on the ammeter as your guide, we will cycle through a variety of currents from 25, 50, 75, 100, 125, and 150 milliamps. Meanwhile, we will record the potential drop across the wire when that current is being forced through it. After the final measurement has been taken, power off the power supply, turn both knobs on the power supply all the way to the left, and then disconnect the circuit. Laboratory cleanup and waste disposal. Before exiting the lab, please refill the carboy and squirt bottle with distilled water, clean and rinse all glassware, stow away all chemicals used in the experiment. Any waste acetic acid and sodium chloride solutions can be disposed of down the drain. However, the conductivity standard solution should be disposed of properly in the marked container under the sink.